I want to present you some examples. So let's assume that we have a geometric sequence like this one, 18, 6, 2, and this sequence has many more terms that we don't see here, all right? And we want to calculate the sum of the infinite geometrical series. So a series, you know that the difference between sequence and series is that the sequence is just a list of elements and the series, it's the sum of the elements, all right? So first of all, if we have a geometric sequence like this one, we have to calculate the common ratio. And you know very well that we need to divide, for example, the second terms and the first term. So we're going to get that it's 6 divided by 18, so it means that it's 1/3. We are actually satisfying the requirement that the absolute value of the common ratio is less than 1. And therefore we can proceed because we know that the sum of the infinite terms that are given by the sequence, it's actually finite. So it means that the series, we say, converges. If this would not happen, we say that the series diverges. Next, we take the formula and we just plug in what's the first element and what's the common ratio. So we're going to have 18 divided by 1 minus 1/3. This means that I will have 18 divided by 3 minus 1/3, which means 18 times 3 divided by 3 minus 1, which gives me 2. 18 divided by 2, it's 9. So 9 times 3, 27. And that's it. The second example I want to present to you, it's a different example. So let's suppose that we have to prove that 0.6 periodic, which means 0.6666 and so on, is a rational number. Now, how to do so? Well, we can express actually 0.6 periodic as 0.6 plus 0.06 plus 0.006 plus blah blah blah. This can be also written as 6/10 plus 6/10 times 1/10 plus 6/10 times 1/100, which is 1/10 squared, plus blah blah blah. So this means that actually I can build a geometric series out of the sum, and in particular actually this is a geometric sequence, right, where the first element it's 6/10, and the second element it's 6/100, and so on. And where the common ratio, we can just take the second element divided by the first one. So we're going to have 6 divided by 10 times 1/10 divided by 6 divided by 10. These element and this element cancel out, and therefore the common ratio is just 1/10. Again, this common ratio here is satisfying the condition for which the infinite geometrical series is going to converge. And therefore I can actually calculate 0.6 bar, which is the value of the infinite geometrical series, as A1 divided by 1 minus R. But the first element of the sequence, it's actually 6 divided by 10 divided by 1 minus R. R, it's actually 1/10. This gives me 9/10 in the denominator. And therefore this gives me, I can cancel out the 10. It's appearing both in the numerator and in the denominator. So it gives me 6 divided by 9. And it's actually telling me that this is, if I simplify, 2/3. I just proved in this way that 0.6 bar, so 0.6 periodic as it's called, can be expressed as 2 divided by 3, which is a rational number. because it can be expressed as a ratio of two integer numbers. The third example I want to present you, it's an exercise that I found in a book. So I just plug it in here and I'll give you some minutes for reading it. So I hope you understood the problem. The ball starts from a certain height, which is 3 meters, and it gets dropped on the floor. It bounces again at a height that it's actually 80% of 3 meters, which is, I calculated before, it's 2.4 meters. And it's going to the floor, and then it's jumping up again, right, to a height that it's 80% of 2.4 meters, and so on. And we have to calculate the sum of these vertical heights. So you have to understand that here I kind of exaggerated that the ball is going to do a kind of a parabola, but in reality the ball is going up and down in the same direction. So the distance that it's going to cover is just going to be the original 3 meters plus 2 times a certain length here that I will call L. Now, in order to calculate the length L, I need to think in terms of a geometric sequence. Each time it's going to bounce up, it's going to be, or down, it's going to be 2.4 meters times 0.8. But the 0.8, it's actually the common ratio, because every time I'm going to jump up and down, I will have a length that I can denote with the label n, and therefore I will have 0.8 to the power of n minus 1. So from this jump on, I will have that jump number 1, it's going to give me a height of 2.4, and then of course I have to come back to the floor, and that's why there is the factor of 2. And then the jump number 2 is going to be 2.4 times 0.8 to the power of 2 minus 1, 1. So exactly 80% of 2.4, and so on and so forth. This means that, of course, I need to calculate what is the infinite geometrical series of a series that has this common ratio 0.8, and where the first element is 2.4. So I'm just plugging in the number. I will have 2.4 divided by 1 minus 0.8, and doing this with my GDC, I will find that this is 12 meters. So to put everything together, it means that the total height that we have to calculate, it's going to be 3 meters plus 2 times 12 meters, which gives me 3 plus 24, which is equal to 27 meters in total.